Other theorems.
Okay.
Welcome all to a special dynamics seminar / colloquium. It's my pleasure to introduce Bowen, who will tell us about the entropy for sofic group actions.
Okay. So thanks for the invitation. And please ask questions at any time. I like it. So I'll start by explaining the problem that I'm interested in, or that the talk will be about. So, okay, I guess I'll start from here. So, throughout this talk, gamma is going to be a group, a countable group. You might think that gamma is the integers, or maybe the free group on two generators. Those will be my two main examples to keep in mind. And, okay, I'll have some probability spaces. So I just mean... Okay, so I just mean a set with a Borel sigma algebra and a measure which has where the total measure is 1. You can think the unit interval with the vague measure. This is sort of the usual example. And I'm going to be interested in actions on this space that preserve the measure. So gamma acts on X, and it's measure preserving. So these are kind of the base assumptions. This is the world that I'm interested in. And so let me explain. When two such actions are measurably conjugate, so I guess I should try to make use of this. Okay, so let's say that we have two such actions. Probably, maybe different measure spaces. These are measurably conjugate. Or isomorphic. If there exists a measure space isomorphism, so this should be an isomorphism of measure spaces. And so it should take the measure of one to the measure of the other and be invertible. And it should commute with the action. So B composed with G should be G of B for G in the group. So is it, okay. I haven't really done much yet, so probably not many questions. Okay, so I'm interested in classifying actions up to measure conjugacy. That's the main, that's the big ambitious goal that's impossible to realize. So I'm going to look at specific very specific class of actions where we can say something, and which are very important for the general picture anyway. Thank you.
Wow.
Okay, so another definition.
Yeah.
So I'll define a very special class of actions that I'm going to be focused on. And they're called Bernoulli shifts, and I'll say what they are. So we'll have a finite set. Yeah.
Sorry, if you use that other chalk,
Okay, yeah.
It's darker. That's the whole time.
Oh, it's darker.
It's darker so people can see it.
Oh, I see.
It's lighter.
Yeah.
That's higher contrast. I can read it.
It's a very dark white.
It's like you turn the air conditioner up or down.
So anyway, I'll have a finite set K of colors. I prefer to call them colors for no particular reason. Okay, so we consider K to the gamma. Now these are just all functions from gamma into K. And gamma acts on this space by precomposition. So the exact formula goes something like this. But it's just colorings of the group and we move it around. Okay. Well, we need a measure, so we'll let kappa be a probability measure on K. Okay, so then once we fix a probability measure on K, there's a natural measure on K to the gamma, which is just the product measure. So for each element of gamma, we have a random variable, and these random variables are IID. They're independent, identically distributed. Okay, so gamma acting on this space is called the Bernoulli shift. Over gamma, and this space is called the base. Okay. So I'd like to classify these. Classify these things up to measure conjugacy. And in fact, this goes back to von Neumann. So von Neumann considers that there was in the 20s, he apparently, it's kind of buried in the literature, but apparently he asked whether or not the two shift is, well, I'll have to say it. So the question is, he was looking at the group of integers. So we look at the integers acting on 0, 1 with the uniform measure to the integers. So this is called the two shift, because you just have two colors or two symbols. And you can ask, is this isomorphic to, say, the three shift?
Equal weights. In what ways?
Isomorphic in the sense of measure conjugacy.
Right.
So is there a measure space isomorphism from this one to this one which intertwines the two actions?
So what's the probabilities we take?
These are uniform measures on these finite
okay,
sets.
yes.
So this is just 1/2, 1/2. This is 1/3, 1/3, 1/3. So he knew that these were spectrally isomorphic. So what you can do is you can look at the L2 space of this, and then you have an operator which acts by shifting, by precomposition on the L2 space. And it turns out that this action on the L2 space is isomorphic to the action of the integers on its regular representation to the countable power. So these are isomorphic in the spectral sense. And at the time that he asked the question, all of the invariants that they knew about were just spectral invariants. So it was not possible to distinguish these two. And so it was a very natural question. Okay. Okay, so the answer came from Komogorov. So he answered this problem by introducing a new invariant called entropy, and I'll tell you what that is. Okay. So, this is going to be very, I guess for the experts, this is going to be somewhat very familiar for the first 10 or 20 minutes, but I'll get to new stuff quickly.
Well, maybe we should check. Anyone who's an expert, raise your hand. Okay, then you can proceed at the current pace. Just let's see.
Yeah, stop me anytime, by the way.
Well, are there any cases when it's obvious they're not the same? Like if we took the two symbols
Yeah.
but didn't have the same weights, like we took a third and 2/3, would that obviously be different, or maybe it's not?
No. At this point, when he asked this question, it could be that all of the Bernoulli shifts are isomorphic. I mean, it was not possible to distinguish any of them.
Because they're all built on the regular representation, you said.
Yeah.
That's what you said, right?
Right. They're all spectrally isomorphic. So there was no way to distinguish them. As it turns out, they are different, but you need a new invariant. Okay. So the new idea comes from, well, its origins are in information theory, and so I'll tell you a little bit about that. So it goes like this. Let's let x mu be a probability space. And let's let y be a subset. And x be a point in x, be random. Okay. And it's random and with law equal to mu. So I want to pose like a very kind of naive, or naive is probably the wrong word, but kind of an intuitive problem. We want to make sense of the following question. Actually, I'll try to do something different. So, how much information do we gain by learning that x is in y? If somebody tells us that x is in y, then intuitively we've gained some amount of information, and we would like to assign a number to that. We'd like to say, 1 bit of information or 2 bits or whatever it is. And
So
we,
if y were x, there would be no information, right?
Yes, that's right. Yeah, if y equals x, then there's no information because we already know that x is in capital X. So, okay. So the idea is that we want a function called the information function, and it should be a function of y. This should be the amount. So it should be the amount of info that we gain by learning that x is in capital Y. So I'm just giving it a name. I haven't said what it is. Well, whatever it is, though, you think, well, it should be a function of a measure of y. It shouldn't depend on anything else because that's all there is. There's no geometry or topology or anything. And the idea is that, well, whatever it is, it should be...
You can also move any set y to any other set y if they have the same mass by observing automorphism in space, right?
Right.
So you can't really, that's all you know.
Yeah, that's the only invariance, right. So whatever it is, it should be non-negative. And I guess it should be measurable, should be measurable. And it should be, one more condition is that it should be, well, if y and z are independent,
What does that mean?
so that means, that means that the measure of the intersection is the product of the measures. Intuitively, it means that if you know that if somebody tells you that x is in y, then you don't have any additional information about whether or not x is in z. And vice versa, It doesn't really change your probability estimation of whether or not y is in z. They're independent. Okay, so if this is true, then we would like that the information that we gain by learning that x is in both should be the sum. And when you think about it, there's only one function that's going to satisfy this. Because what this tells you is that, well, if we think about it as a function of a real number, then I of t times s has to be I of t plus I of s.
Wait a minute, I'm getting a hint.
So it has to be the logarithm function, right?
Right.
Oh, I thought root 2 sounds low. I guess that.
Okay. So it just has to be the logarithm of the measure. And it's traditional, I guess, to put log base 2 and put a minus sign. So it's a non-negative number. And then log base 2 means that, you know, if y has half of the measure, then this is 1 bit of information. You know, so, right, it's very, I guess, intuitive that if you cut it up into 2 pieces and I tell you it's on the left or I tell you it's on the right, then you gain 1 bit. Right? Okay.
That's the warning about the colored chalk. It never can completely erase it.
Yeah. Have to do this. Okay. Okay, so if I have a random variable, more generally, so if maybe now I have a function on x into k, and k is a finite set. Then you might ask, what's the average amount of information that I gain by learning the value of the function? Okay, so
Average over what? Over the x?
yeah, over x,
Ah.
or the expected amount of information. Okay, so the expected amount of information, which I guess in this formalism would be the inverse of a point. But anyway, I don't want to write all this out. So I'll just say it in words. The average amount of info from learning phi of x, well, that's going to be, sum over all possible values. We'll take the measure of the pre-image, and then take log base 2 of the measure of the pre-image. And I guess we need a minus sign to make it positive. So, does that make sense?
The inverse of k is really small, and you knew it with that k, then it would be a lot of information.
Yeah, that's right. Yeah. So, right. So here's our space X, and all that we've done is we've said, okay, we partition it into some number of pieces, maybe 26.
Those are your colors, right?
Yeah, those are my colors. Right. So, you know, maybe I've got this one is whatever this color is. Anyway, you see the idea. Then, by learning what you know, the average is just going to be the okay. So maybe I should say a more specific example. So, for example, if the push-forward measure is uniform on the set of colors, so if each color is getting the same measure for the same weight, then this, which is called the entropy of the random variable, then the entropy of the random variable is just log n, or just log of the number of colors. So, for example, if you're just flipping a coin.
1 over k in k terms, is that why?
Yes, that's right. Yeah. Yeah, right, because this is just 1 over k and this is 1 over k. So for example, flipping a coin, the entropy in flipping a coin is going to be log 2. And rolling a die will be log 6.
Fair die.
Yeah, fair die, right? Okay.
What if you're mapping to a continuous probability space?
Then,
Can you still do something?
yes, you can. So, well, if the push forward measure is not supported on a countable set, so this makes sense for a countable set, but if it's not supported on a countable set, then the entropy is infinity, by definition, or you can justify it as well. It's just saying, well, it's it's the amount of information. You have sort of an infinite amount of information. If x is the unit square and I tell you it's x coordinate or it's y coordinate,
It's too much information.
you have an infinite amount of information. Yeah.
But couldn't you have a measure biased entropy? I mean, you could integrate with respect to some measure on K.
Sure.
Then you'd still be all right. It's not countable.
That's right. Yeah. I mean, I'm biasing with respect to counting measure on capital K. Okay. So what does this have to do with dynamics? I will tell you next. So let's suppose that we now have a transformation, which is preserving the measure, and let's say we also have a function into a finite set. Then we can consider not just the entropy of phi, but also phi composed with t, and phi composed with t squared, etc., up to some amount of time. So by this, what I mean is that we have, I consider this to be a random variable itself, this n plus 1 tuple. Right? This is an n plus 1 tuple that maps into k to the n plus 1 power. Right? Okay, so it makes sense. So I can talk about right, this is just a map from x into k to the n plus 1. Okay, so I can think about the entropy of this, and it might be that all of these are independent. And if these are all independent, then the entropy is going to be additive. And so you'll just get n plus 1 times the entropy of phi. That's a consequence of this independence feature. But in general, they're going to have some dependencies, and so the entropy will actually be less. There'll be, once you know phi, you might already know something about phi composed with t. In fact, it might even be deterministic. You might already know what it is. So in general, you expect this to be sub-additive, and it is. So what we do is we divide by n plus 1, and we take a limit. And this is called the entropy rate. So it's kind of entropy per unit time. So it has a physical interpretation. You can think, well, we're doing some kind of experiment, and at every unit of time, we take a measurement, which takes values in a finite set. And, maybe our experiment is as random as a coin toss, just tossing a coin at every unit of time. And then you'd say, okay, that's log 2 entropy. But maybe it's very deterministic in the sense that, once we've been flipping the coin for a very long, once we've been taking our measurements for a very long time, we have a pretty good guess of what happens next. Then the entropy would be very small. So it's a kind of measurement of the amount of randomness or unpredictability in the system. Okay. Any questions?
So the entropy rate is now also going to be called the entropy?
Okay, yes. So that's the next definition.
So should we think of this as a measurement of t or a measurement of phi or both of them together? I guess t is the next step.
Yeah, well, we'll let phi vary. So we'll just take the sup over all phi. So phi here can map x to any finite set. Not necessarily k. This doesn't have a k on it, right? This is just some. So that's the entropy of the transformation.
Sup over phi.
Yeah.
No, just this.
Okay,
The
so
entropy rate called the entropy of transformation. Yeah.
right.
Information rate.
Okay. So this is also called the Komogorov Sinai entropy. And Komogorov proved the following in 58. The entropy of this Bernoulli shift action I should maybe tell you, if you look at it this way, it looks like it's an impossible thing because you have to take a sup and, it looks like an infinite calculation. But actually, it turns out that this is equal to ht of psi, where psi is any generating function. So, I'll write it this way. So for any psi, with the property that the sigma algebra generated by the Brook action and psi is, all Borel sets.
Mod u.
Yeah, modulo sets of measure 0, which I'm always ignoring sets of measure 0. So this is actually Komogorov's theorem. This is, it takes some work to prove this, but once you have it, it means that, it becomes a very easy to compute number because you just pick your favorite generating partition and do this computation. And that's it.
You need that limit computation there.
Yes. I mean, this is still a limit, but
Yeah.
you don't have to worry about all partitions, all observables, Sometimes I call these observables. Okay.
Sorry, which things do you call observables?
This is okay. So he computed the entropy rate of the Bernoulli shift. It's equal to the entropy of the base space, which is defined to be just the entropy of the identity map from K to itself. So
log mu thing.
yeah, this thing, right? Right, exactly. So for example, the 2 shift has entropy log 2, and the 3 shift has entropy log 3. So they really are different, as you'd expect.
This problem was open until that time.
Yeah.
From the 20s to the 60s.
Yeah.
And I'm assuming you forgot to mention, or I misheard, that your entropy is an invariant of the isomorphism class of the dynamical system.
Yes. Writing it like this makes it very makes it obvious that it's an invariant. The non-trivial thing is proving this. That it's equal. You don't actually have to check over all partitions, just or all generating. I mean, you don't have to check all fees. You just need to check one that's generating.
So for these shifts, the obvious partition is generated partition.
Yes.
The first thing.
The obvious map that you choose is the one that's just projection onto the identity coordinate. Right. So it's just k of a function is just the value at the identity. I guess I should say x0. Yeah, and once you know this theorem, this is just a trivial calculation. It's really It's something everyone can do. Okay. Okay, well, let me explain one more fact about this. I need a definition. Entropy has become, one of the most important invariants in dynamical systems. And one of the reasons why is because, well, you can compute it, all kinds of operations that you perform on dynamical systems, on automorphisms. You can see how the entropy transforms and so on. But I'm going to focus on something else. So let me explain this. Suppose we have two actions. So suppose we have these two actions, and we have a map from x to y, which pushes forward the measure and intertwines the action, but doesn't have to be invertible. That's called a factor map. So then we say that this system is a factor. Is a factor of the source. And it's pretty, entropy, in the case when the group is the group of integers, one can see that entropy cannot increase under a factor. The entropy of this can't be larger than the entropy of gamma acting on x. So, at least in the case of the integers, this is always true. Well, that's because anything that's a random, if you have a function on y, you can always pull this back to get a function on x. And the entropy rates are going to be the same. That's the technical thing, but you can also just say, well, it makes sense on an intuitive level that we should have more information here. This one is kind of like, well, you're putting on blurry glasses or something, so you're not getting as much information.
Can you quantify the information loss in terms of the function phi?
Well, the entropy rates for these two are the same.
So there's no loss.
It's just that there's no loss, but you might have functions which are, up here that are not pulled back from functions here. That's why this one can be larger.
Is the entropy loss can be expressed in terms of some fiber action?
Oh yes, yeah. You have a notion of relative entropy.
So then you can actually have an equality, like that entropy equals this entropy plus this term in terms of the fibers?
Yes. Yeah, there's a relative entropy notion. Okay, so I just wanted to point out one simple consequence of this, is that if we have gamma acting on the 2 shift, 0, 1, with the uniform measure, we have z acting on this, this cannot factor onto, let's say we have 4 symbols, right? Because entropy would have to increase. This has entropy log 2, and this one has entropy log 4, and entropy would have to increase. So one nice thing about entropy is that it also tells us it also tells us that something cannot factor onto something else. Gives us an abstraction. I should maybe mention, that was Komogorov's theorem in 58. In 1970, Ornstein proved the converse, that Bernoulli shifts are in fact classified exactly by entropy. So if they have the same entropy, then they are in fact measurably conjugate. It's a really, it's a deep theorem, and it's highly non-trivial. Okay, so what I want to explain now is that for the free group, so now we consider gamma equal to the free group, that this fails. And this...
It's something is a
That's a
factor
problem.
it's not supposed to be. Something is a factor that's not supposed to be.
Yes, yes. This fails. If we replace these z's with gammas, we do get a factor now. Okay, and I'll explain why. So the free group on two generators is you can visualize it as the four regular tree. This is its Cayley graph. And if we consider 0, 1 to the free group, so a point in here consists of labeling all of the vertices with labels in 0 and 1. So like this one might be a 1, this one might be a 0, maybe this one is a 1, and so on. Right? Maybe this one's a 1, and this one's a 0, and so on. Okay, so from this initial data, I want to construct labels on the vertices that take place in 0, 1, 0, 1. So I want two labels on the vertices. And the way that I do it is I take this one and I add it to the one north, mod 2. So this one is going to get 0. And I'll take this one and I'll add it to the one east, mod 2. Okay, and I'll do the same over here. So this will be 0 plus 1 is 1, and 0 plus 0 is 0. Okay.
I mean, if
and I'll keep doing that everywhere.
since we're working by 2, you could think that you subtracted also.
Yes, that's right. Probably that's a better way of thinking about it.
Fine.
Well, you can do this game and for Z mod PZ if you like. Okay, so this actually factors onto this one, and in fact, what's going on? You can see this more general picture.
So that map is a subjective equivariant map.
Right. Right. So we have a subjective equivariant map, and you can think of this as a compact group. Z mod 2z to the gamma, so it's just the direct product of copies of z mod 2z. And this is this map that I just defined by pictures is a surjective homomorphism. It only has a kernel of 2 points. All zeros are all ones. So it's in fact a 2-to-1 factor map. And it's for that reason that so Ornstein and Weiss produced this example, and many of the experts thought, well, there can't be any entropy theory for the free group because of this reason. I did a bit more some work on this, and I showed that for the free group, in fact, all of the Bernoulli shifts factor onto each other. Once you have this example, you can see, well, we can go one step further and push by ignoring the first coordinate and playing the same game on the second coordinate. And we can repeat that, and so you can get a map from the 2 shift to the infinite entropy shift, the one that's over a Cantor set. And then you can factor onto anything from there. Okay. So it was no big question whether or not these two are actually isomorphic.
What year was this?
This was 87. Ornstein and Weiss. They had this 170-page article, and this problem appears at the end. Open problem. Okay. So, yeah, okay, so actually, how much time do I have? Is it till 3:30?
Yes.
Okay, so let me explain a little bit of motivation for how to solve this.
Well, what's the question now?
So the question is, are these two in fact isomorphic? So is the 2 shift over the free group, so gamma here is always just the free group, is this, yeah, let's do it like this. So is this isomorphic to the 4 shift?
I suppose you can factor back the other way in some trivial way.
Yeah.
Right? You have factors both ways.
Yeah, you definitely have a factor this way because you can just ignore the first coordinate, say. And so these factor onto each other. Okay. So let's see. Right. Okay. So back to the integers. I mean, I'll explain the solution to this, but it'll be useful to go back to the integers and reformulate entropy a little bit.
Is it conceivable the spectral invariance might distinguish these?
No. These are, it's the same game as in the integers, that the Koopman representation here is isomorphic to the countable sum of not regular representations. Okay. So back to the integers. Okay, so I want to tell you again what's the entropy rate of a random variable. And this time, suppose that we have a Markov chain. So these are very nice systems. Suppose that this pair is Markov. Markov, what that means is that the law, okay, I'll say it this way. Suppose that I'm performing some experiment, and I've been watching it for a very long time, like infinite time, and I've watched all of its values, and now I need to make a prediction what's going to happen next. And you say, well, in fact, I just need to know the last value. And in fact, the rest of the time, that's totally irrelevant to what's going to happen next.
Like a 2-year-old. Like a 2-year-old.
Yeah, like a 2-year-old. Okay, so that's what it is. The law of phi conditioned on its past is the same as the law of phi conditioned on its immediate past. That's a Markov process. In this case, it's easy to check that the entropy rate is equal to the entropy of, okay, the present together with the past minus the entropy of the present. That's, another way of stating this, which is equivalent, you can take it as a definition, is that this is the entropy of phi conditioned on its immediate past. Relative to its immediate past. Okay, but what if it's not Markov?
You say you could take that bottom symbol as the definition?
Yeah.
The upper symbol is the definition of the bottom symbol?
Yeah, you can. It's not the nicest way to go about things, but you can. Okay, well, what if it's not Markov? Okay. Then what we want to do is approximate it by a Markov process. Okay, so I'll explain. So in general, if we have a finite subset of a group, and we have a random variable, then we consider phi to the f as a random variable from x to the k to the f. So what it is it takes the point x to the map, which sends my group element into phi fx. I'm saying it this way because I'm going to need to use it again, but let me just tell you something that's maybe a bit more intuitive. So, for example, phi here, in the case of the integers, we have phi to the 0 n that means that I look at this compound random variable. Right, so this is a map from x into k to the n plus 1. So it's just some shorthand notation. And it's a theorem, and it's very easy to prove that in general, not assuming Markov or anything, this is obtained as a limit.
Is that a T or a gamma?
T.
H of T, H of gamma? What is
This one, this is a T. This is a T for the transformation.
Okay.
So the entropy rate of this random variable is just the limit of what we would get if it was a Markov chain. So it's going to be phi composed with a T. That's what we want. Except I'm going to have to change this because it's not a Markov chain. So what I do is I replace this phi with phi 0n. And now it's a correct statement.
In a Markov chain, you have T inverse. Your definition of the Markov, you have T inverse.
Oh, yeah, sorry, I'm mixing my T's and T inverses. It actually doesn't matter. I mean, everything's going to work either way. But, probably this should be an inverse just for the sake of equivariance and whatnot.
But the idea here is you recording the total path as your state, so therefore it's Markov. So, this doesn't have to be a Markov process, but what I'm doing is I'm looking at a Markov approximation, which is an n-step Markov approximation. So I'm just saying, an n-step Markov chain, what's that? Well, Oh, I see.
that's saying, the law of the random variable given the infinite past is the same thing as the law of the random variable given n steps back in time. If I have an arbitrary system, I can approximate it. I can say, I look at the n-step Markov process that has all of the same marginals. That has the same. It has the same distribution Okay, so this is kind of a suggestive idea for the free group. So back to the free group. So free group on the two generators, and I'll just call that gamma. And I'll try to be careful so it looks like a T. Okay, so suppose that I have gamma acting on some space, and I have a random variable. And it does make sense to talk about Markov chains over the free group. I'll explain that in detail maybe if there's time. But it does make sense. And so one might think, if this was a Markov process, then what I would want the entropy to be is something like this. Say I take phi, I take this composite random variable. So this is one direction, and I want to add it to the other direction. Well, sorry, I should be subtracting, right? Yeah. Okay, because I have these two directions, but if you think about it, this isn't quite the right thing, because this is like, I have entropy in the A direction, entropy in the B direction, but somehow I've counted the vertex twice. And so I'll subtract one more of these. Okay, so this is kind of like what I think the entropy would be if it was a Markov chain. In general, what I want to do is I want to replace this phi
with phi, I need to put, I need to join it with translates of itself. And I guess the natural thing to do would be take the ball of radius r and take the limit. So the ball of radius r is just a set of all group elements that have length at most r.
Word length.
Word length, yeah.
Counting A inverse by something like that?
I'm sorry?
Is this ordered? A and A inverse have the same length?
Yeah, they have the same length. Yeah. Actually, I don't think it's going to, it won't matter. As it turns out, this is the same thing as taking the infimum of f to the phi of w, where w ranges over all finite subsets.
Overall what?
Over all finite subsets. So it doesn't actually matter. Okay, so the theorem is that this thing is pretty good. If phi is and psi are generating, so generating means that the sigma algebra generated by phi, so for example, the sigma algebra generated by phi in group action is, all Borel subsets of X. Then they get the same F invariant, or they give the same F entropy. So this is an invariant of a dynamical system. And we can compute it in the special case of Bernoulli shifts. And we can show that it equals the Shannon entropy. And so the 2 shift is not the 4 shift. They are different. And another interesting feature is that in the special case of Markov chains,
What's the year of this result?
it was published in 2010. It's my result.
So that every 20 or 30 years there's a new statement of Komogorov, Weiss.
Yeah. Okay. Well, I'll give an example. An example of how weird things can be. So in this example, I'm going to have a parameter epsilon, which is just some positive number, I guess. What I'm going to do is every vertex is going to get a +1 or a -1. And the rule is that I first flip a coin. And this one is a +1 with probability 1/2, -1 with probability 1/2. Okay. And then whenever I cross an edge, I change the sign with probability epsilon. So epsilon is the transition probability. So maybe I change the sign here, or I could keep the sign, with probability 1 minus epsilon, independent of everything else. So I generate a random function from my free group into 0 and 1. So this is the Ising Markov chain related to the Ising model. And this is a Markov chain, so I can compute the F invariant precisely because it's just capital F, and that's a finite computation.
Again, I didn't picture it. You can what?
I can compute the F invariant for this precisely. Because it turns out that I didn't write it down, but for Markov chains, if I put in a Markov process here, that's equal to capital F of the same process.
For the what?
Capital F. The point, right, you have this capital F and you have this little f.
Okay.
And capital F is just a finite calculation. Little f is a limit, so it might be more complicated. So for this one, F invariant of the Ising with transition probability epsilon,
I wrote it down. I mean, it's an easy computation, but I forget. And I'm just writing it down just to show you that it's very explicit, but also because there's a very interesting new phenomenon that occurs. Consider the special case when epsilon equals 0. In this case, there's only two states. It's either all plus ones or all minus ones because there's no transitions. And when you look at it, this vanishes and this vanishes, so you just get minus log 2. And so that's supposed to be the entropy for this system. And even when epsilon is small but positive, you're going to get a negative number. Okay, there isn't a whole lot of time, so I'll give a kind of overview of why this happens. It turns out that
so your entropy is going to be the negative.
Yes, it can be negative. It can be negative, and it can increase under factors. So there's some unusual properties. Okay, so
did you decide whether or not the free group case was different from the integer case? You mentioned it as a question.
I'm not sure what you mean.
There is this theorem which distinguishes.
Well, yeah, it's not really different in the sense that it turns out that Bernoulli shifts over the free group are completely classified by this F invariant, which is the base entropy. So,
can you give some intuitive idea of what negative entropy means?
Yes.
That's
what I'll do next. That's what I'll do next.
Negative.
This is going to take a little bit of time, but I hope not too much. So suppose I have a map from my free group into the symmetric group on n things. Okay, so the reason why I'm doing this is because this is going to give me a kind of finite model for my group. And I want to reduce everything to a finite computation and then take a limit. Okay, so a map. Actually, let's say that we have a finite subset of my group gamma, and I have an epsilon positive, not the same epsilon. Let's call it delta. Okay, so a map from my finite set, so this is just a set 1 through n, into K, the colors, is, it's W delta sigma n, let's say phi here also, good, if it gives you a good approximation to your original system. And what that means is that the local statistics should be close. So what that means is that if I take a uniform random variable, if I take the uniform measure on this set, and I take psi, and I push forward the measure, okay, so I should say it this way. Psi sigma W is now a map from 1 through n into colors to the W. So it takes a vertex V into psi of, into the map that sends little w into, this should be a capital W, to sigma n W V psi. I can give an intuitive explanation for what's going on.
I don't like these precise explanations.
Okay. So, well, let me give you a more intuitive definition then. This psi n, okay, so it's some map from gamma into the symmetric group. From this we can form a graph. So the graph
is just to set vertices 1 through n. And we have an edge from one place to another if sigma n of A at this one takes this one to this one, for example. So we just put in the generators. This is like a Schreier coset graph, if you will. Okay, so we're going to have.
If either of the generators do that, or
Yes, if either generator does this, right? So we'll have.
look like the cable
We'll
graph,
have two kinds of edges. One's labeled A and one's labeled B. So A takes this one to this one, B takes this one to that one, etc. Whatever it is. So we get some four regular graph because it's because we have two generators. Then what we're going to do is we're going to look at functions from the vertex set into the set of colors. So now you can think that these vertices are colored. Now I take a vertex at random, okay, and I look at the ball of radius r centered around that vertex. And so that gives me a coloring on the ball of radius r. And it's random. Well, I want the probability distribution of that to be close to the probability distribution for my original map.
the original map from where?
So originally I had a map from x into k. So if I take a point here at random, and then I move it around by the ball of radius r in my group, then I look at the colors of that. So this map gives me a random coloring of my group. So I want to compare the probability distribution of the random coloring, at the origin, compared with this. And if those distributions are delta close, then I want to say my map is delta good, or it's a good approximation.
How is x related to your graph?
This x?
Yeah.
Sorry, this x is, okay. This is gamma is acting on x mu. And b is a map from x to k. Yeah. Okay, so this f invariant, what it is it counts the number of good maps. So you count the number of good maps. You have some parameters, W and delta, sigma n, etc. You count the number of good maps, you take the exponential rate of growth. You expect that this will grow exponentially. There's something I haven't told you, but I will tell you in a moment. This turns out to be the f invariant. I haven't told you how to choose these maps, these sigma n's. You have these sigma n's from gamma into the symmetric group. What you do is you choose them at random. Once you've chosen where the generators go, that determines the map because it's a homomorphism. We only have two generators, so there's there's n factorial squared homomorphisms. The n factorial choices for the first one, n factorial choices for the second one. So there's only a finite number. We just choose them at random. Then here, we don't look at the number, we look at the expected number of good maps. Now what happens is that typically, if you choose a homomorphism from the free group to the symmetric group and you form this graph, typically this graph is an expander, which means that it's not possible to divide it into two pieces where you have a small number of edges in between, of roughly equal sizes. And but sometimes you can. It's rare, but it happens sometimes. The rate at which that happens is about 2 to the minus n. That's why the entropy is minus log 2 for the Ising model with zero transition. Okay. This kind of explains why you get a negative number, because this number can be between 0 and 1. Logarithm of a number between 0 and 1 is negative, and that's why it happens. Okay, I guess that's it for
Is
the
it
time.
like it's a lot of rigidity or not chaotic or something when it's the negative? You don't have a lot of, you're saying you don't have a lot of these good maps.
Yes, that's right. Yes. Well, there are different ways in which you might not have some good maps that can occur. And even the value minus infinity can occur here. For example, the action of the group on its profinite completion. On its profinite completion. So you look at, that has f invariant minus infinity. It's because you just can't model the profinite completion very well on a random, on a random quotient, finite quotient of the group. There's a lot of open problems. It's not. Well, I should say one thing. Okay, this interpretation, it turns out, generalizes to a very large class of groups, including all linear groups. So it generalizes to sofic groups, which includes all residually finite groups. So, SLNZ and mapping class groups and many of your favorite groups. You just need a sequence of good models, finite models to your group. So as long as you have a sequence of finite graphs, which are converging to your Cayley graph, in the sense that when you choose a uniformly random vertex and you look at the ball of radius r, what you see looks just like your Cayley graph. Like the ball of radius r in your Cayley graph, with high probability. Not always, maybe, but with high probability. If you have a sequence of finite graphs like that, then your group is called sofic, and this entire machinery can be generalized, and you have classification of Bernoulli shifts for sofic groups, because you have an entropy theory there.
Are there any non-sofic groups that you know of?
No, this is an open problem.
What?
It's not known if there are any non-sofic groups.
Maybe every group is sofic.
Yeah, it's conceivable at least.
Then your theory worked for all groups.
Yes.
And the best thing about it would be counterexample to Dromov's axiom.
Yeah.
Group theory.
Yeah, most people think that there must be a non-sofic group out there. We just don't have the right tools or something. I don't know. I think it's it's an extremely subtle problem. It's hard to know.
Thank you for teaching us.
Any further questions or comments? Speaker? No, we can thank you again.
What is your dream question of what we really like to understand further than that?
Well, one of my favorite problems that's still open is if you have a fixed action of a sofic group, but you have two sofic approximations. So I didn't really get into it very much, but the entropy theory for sofic groups a priori depends on a choice of sequence of finite models for a group. And this sequence of finite models is called the sofic approximation. So your entropy could depend on the sofic approximation. In fact, it really does. There are examples. But if you exclude the value minus infinity, so if you say, okay, if I have two sofic approximations and I look at one action and I look at the sofic entropy, and neither one of these is giving me minus infinity, then do they have to be the same? That's an open problem, and it would be very exciting. These kinds of problems occur in these statistical mechanics models on random regular graphs. Because a random regular graph is basically the graph that I worked on. This is the same thing.
Random regular graph.
This is a random regular graph, and there's a lot of literature on random regular graphs. And you look at like the Ising model or something on the random regular graph, and the partition function, and you would like to know, well, okay, let's ignore the word random if you just have a sequence of regular graphs which is converging to the tree, so it's locally very tree-like, do the asymptotics of the partition function depend on the choice of sequence? That's the, yes it does, but excluding the possibility that you just don't have any models at all, then maybe it doesn't.
Let's thank the speaker again. We're going for dinner and we can ask more questions. Then, so let us know if you're planning to join.
Just talk to me if you want to join us, but you can just.
Yeah, let me show.